Okay, so I think I'll start with the introduction. It's 8 o'clock. So good morning, everyone. Good afternoon, and also good evening, wherever you're joining us from. Thank you for joining us today. I'm Mary Salvana, Assistant Professor in the Department of Statistics at the University of Connecticut in the United States. On behalf of the organizing team, I'm pleased to welcome you to this series, High Performance Statistical Computing Presentation Series. Each seminar runs for 60 minutes. The speaker will present for 45 and followed by 15 minutes of questions. Please feel free to type your questions into the chat at any time. We will collect them and raise them during the Q&A. All talks are recorded, and the recordings, along with the slides, will be posted on our website. We typically host one seminar each month, and you're also welcome to nominate future speakers. To stay updated on upcoming events, you can subscribe to our mailing list, and you'll find those details as well as other resources in our website, hpsc4science.org. Before we begin, I'd like to briefly mention that we also have an invited session at JSM 2026. The session is called High Performance Statistical Computing, Challenges, Opportunities, and Future Directions. The session will be on Thursday, August 6, 2026 from 8:30 a.m. to 10:20 a.m. in Boston, Massachusetts. So that's where JSM is going to be this year. We would be delighted if you could join us also for that session. With that, I'll introduce our speaker for today. Ying is a professor of statistics at KAUST, Saudi Arabia, and a 2025 Fellow of the American Statistical Association. She received her PhD from Texas A&M University, completed postdoctoral training at the University of Chicago and SAMC, and joined KAUST in 2014. Her research focuses on spatio-temporal statistics, functional data analysis, and environmental applications. She is an elected member of the International Statistical Institute and has received several major recognitions, including the ASA Statistics and the Environment Early Investigator Award, the Abdel El Sharawi Young Researcher Award from TIES, and the 2024 ACM Gordon Bell Prize in Climate Modeling. We're very pleased to have Professor Sun with us today. Ying, thank you for joining us, and the floor is yours.
Thank you, Mary, very much. Thank you very much. Hello, everyone, and thank you for getting up early if you're in the US. I'm Ying Sun from KAUST. Mary mentioned HPSC, High Performance Computing, Statistics Computing. I think it's a brilliant idea to bring people together to have this new community, because I think statistical computing itself is a very exciting research area. The high performance computing, high performance statistics computing sounds more even cooler, right? So I'm also very happy to be part of it. So in the organizers, I will especially thank Mary, Sammy, and Yan, those young researchers. They lead this new community and organize all the seminars. All of us will benefit from it. So today I will talk about a few projects I did with my former students, and also Sammy, the senior research scientist, to show some examples of using HPC or deep learning for statistical computing, especially for spatial-temporal statistics. I always feel I'm still new in HPC, but when I think about it, actually since 2017, I already started several projects using HPC. So here today I would select a few examples to show how HPC and deep learning can help basically fitting a Gaussian process to large spatial-temporal data. So I will share my screen. Okay, since I think maybe not everybody is in spatial-temporal statistics. I will give a brief background and motivation, talk about the challenges, computational challenges in spatial-temporal statistics. Then I will mention a few innovative software tools we developed over the years, including ActualGeostat, Parallel Vecchia GP, Gaussian process, Parallel Block Vecchia GP, Parallel Scaled Block Vecchia GP. At the end, I will talk about two examples using simple deep neural network to help spatial prediction and spatial temporal forecasting. As we know nowadays, we do have a lot of massive high dimensional data. When we collect data, the data are indexed naturally by space and time. So we often have a spatial temporal data set. So that's why spatial temporal analysis become more and more important. As I mentioned before, today I will talk about several advanced statistical methods or computational methods we developed to solve complex problems in spatial computing. I give one example here about geospatial dataset. So in this animation, I showed hourly wind speed over the Middle East. So as you can see, we do see some dynamics in space and also time. So these dynamics are driven by the dependence in space and time. In spatial temporal statistics, one major question or topic is to model or understand the dependence in space and time. So this is we so-called spatial processes. So sometimes we may have more than one variable observed at each location. So for example, when we talk about wind speed, we have wind speed and also wind direction. Typically, we may consider two components, UV component. U component means it's parallel to the x-axis, and the V component means it's parallel to the y-axis. So if we consider such two components of wind speed, we have a bivariate spatial data set. So this is so-called multivariate spatial data. So for example, here I give the decomposition of wind speed along x and along y. So naturally, we have a bivariate spatial process for the wind. So in geostatistics, we call this a multivariate spatial processes. I listed several fundamental problems in environmental data science. Typical goals associated with modeling geospatial data include statistical inference, typically is estimation problem, or stochastic simulations. When we build an emulator, we can simulate from statistical models. The last also typically is pretty important, is about prediction, spatial interpolation or spatial temporal forecasting. In spatial statistics, for example, Gaussian process models are fundamental and often serve as building blocks for more complex models in this analysis. But as we know, they face certain limitations and challenges in modeling and computations. As we know, Gaussian processes are fully specified by its mean function and the covariance function. So in terms of modeling, how to specify a covariance function becomes important because covariance function describes or characterizes the dependence of the process. In terms of computation, once we have a Gaussian process, we can write down a Gaussian likelihood for inference. So as we know, when the dimension is high, the Gaussian process, the Gaussian likelihood suffer computational bottleneck. Kriging is a spatial prediction problem in geostatistics. In terms of computation, it also has it can be time consuming. So I will mention this a little bit in the later in the talk. In terms of simulation, similarly, if we want to simulate data from a given Gaussian process or Gaussian random field, the computation can be also high. So here, suppose I give some notations just to talk about the covariance function I mentioned before. Now, if we suppose we have a multivariate spatial data, here the P means the divisionality. For the wind example I mentioned before, the P is equal to 2. We have a bivariate spatial processes. For simplicity, I assume this multivariate spatial process has a mean 0 and a p-variate random field defined on a d-dimensional space. Then since we have a multivariate spatial field, then the covariance matrix or covariance function is a matrix valued multivariate covariance functions. So that means if we have a bivariate spatial random field, marginally we will have a spatial covariance function, and we will have another cross covariance functions. So this CII here denotes marginal covariance functions, and the CIJ, when I is not equal to J, denotes cross covariance functions between the two distinct process components, Xi and Xj. For the wind example, the cross covariance describes the dependence between U and V component. So another example is if we observe, for example, PM 2.5, the air pollution and wind speed. So this cross correlation will cross covariance function will describe the dependence between air quality and wind speed. For space-time, the covariance function definition is very similar. If we assume X as a ST is a zero mean spatial temporal random field, then the spatial temporal covariance function is defined in the following way. So if we consider the same location, then we will have a purely temporal covariance function. If we have we consider the same time point, then we will have a purely spatial covariance function. So as you can imagine, when we have a multivariate spatial field or space-time data, the covariance function itself becomes much more complicated because we need a realistic way to characterize or to model the cross covariance function. So for example, in space-time setting, we may have a symmetric or asymmetric spatial temporal covariance function. In the multivariate setting, we may have a asymmetric covariance function among those variables. So there are some challenges in modeling, as I mentioned before, because not all the functions can be used as a covariance function for multivariate spatial random field. It has to be non-negative definite. So the choice of functions for modeling covariances is limited to the class of non-negative definite functions. Oftentimes, the existing class of models lacks the flexibility in different aspects, such as I mentioned the cross-spectral features in the multivariate cross-covariance function may not be realistic. So it's necessary to propose a new class or richer class of cross-covariance function to be able to describe the realistic cross dependence in the process. And another example is asymmetric cross dependence in the cross covariance function. And the non-stationarity is always a big issue in the covariance modeling. So that means the dependence will change in space and along time. Okay, so now we talk about computations. If we have data observed from a Gaussian process, now we go back to univariate case, P is equal to 1. Suppose we have n irregular space observations from a zero mean Gaussian random field with a covariance function C, then the data vector of size n will follow a multivariate normal distribution with dimension n. So this is a log likelihood of a multivariate normal distribution. So as we know, the classical way of evaluating this log likelihood is to do collective decomposition of the covariance matrix. This covariance matrix is of size n by n. So once we get the collective factor, then it's easy to find this quadratic term and the deterministic also. But collective factorization requires n cube floating point operations and n square memory. So remember, n is the number of locations So when N is large, the computation become challenging. Then the Kriging is basically is a best linear unbiased predictor plumb in statistics. In geostatistics, so-called Kriging. Kriging is a condition. We use a conditional mean as the prediction. So when we observe x1 vector and we want to predict x2 vector given all the observation in x1 vector. So we use the conditional mean as the prediction. So Kriging with conditional mean of this form is our prediction, and the associate variance is the Kriging variance, which represented here. So from the formula, you can also see the computations become challenging for large N. N is the size of the x1 vector, and also the number of locations you want to predict is M. If this location, those locations also has, if the number is large, the computation is also become challenging. So this is a prediction problem. Sometimes we may need a simulation from a given Gaussian random field. So the simple way to simulate correlated data is we generate an IID from a standard normal distribution. Then we know the covariance functions. We need to construct the covariance matrix based on the given covariance function. So once we know the covariance function, we need to calculate the cholestic decomposition of this covariance matrix. Then once we have this cholestic factor, we can multiply by the IID normal 0, 1 data and get correlated data which has the covariance matrix sigma here. So as you can see, when we need to simulate data from a random field, we also need this cholestic decomposition. So computations become very challenging for large number of locations. So those are the computational challenges in fitting a Gaussian process model to large spatial data. So here I give several examples of Gaussian random field simulated from a zero mean Gaussian process with a Matern covariance function. So as we know, Matern covariance function has 3 parameters: the smoothness and the range and the local variance. So I don't need to show the value of those parameters, but from all these examples, we do see several images looks pretty realistic as certain physical processes. So our statistical inference, the goal is to estimate all these 3 unknown parameters from the data we observed. Okay, so those are the challenges in inference and prediction. To solve these problems, we tried different ways. So first, many years ago, we proposed ActualGeostat, which is a software to perform exact computation for Gaussian processes. So today I will focus a little bit more on the vector approximation. So later I will give more details. So I will talk about vector approximation on GPUs. So we call it a parallel vector GP. And to make the computation even faster, we propose a new algorithm called parallel block vector. And later, motivated by high-dimensional Gaussian process computation, we propose a vector for on multiple GPUs. We call it a parallel scaled block vector. And then for the second part of the talk, I will talk about deep Kriging we proposed a few years ago. Is similar to the goal is exactly the same as the Kriging in geostatistics. Deep Kriging simply means we borrow deep neural network to help with the spatial prediction problem. So ActualGeostat, I just gave one page very brief introduction. HPC, as we know, can help with fitting a Gaussian process model to large data sets when the number of locations is large. The actual geostat software provides extra scale geostatistical computations. The software is available on GitHub. So because the number of locations, sometimes nowadays it's very easy to get a large number of observations. So just think about like 100 by 100 grid. If we have irregular space locations in this area, we already have 1 million locations. So in the past 10 or 20 years, various of approximation methods have been proposed in the literature just to solve this fundamental problem, how to reduce the computation in this multivariate normal likelihood evaluation. So in KAUST, since 2022, we organized the computations on spatial statistics for large data sets. We investigated the performance of different approximation methods, which with large data set generated by actual geostat. I think the data set itself are very valuable. You are very welcome to test your method on this data set, because one challenging problem I mentioned before is the statistical simulations. So to be able to simulate from exact covariance functions on large scale is not easy. So actual geostat provides a tool actually can generate a large spatial temporal data set with exact covariance structure. Now I will talk about vector approximation. Vector approximation is a very general idea. So the basic idea is the multivariate normal likelihood can be written as, if we talk about log likelihood, can be written as a sum of log conditional probabilities. So when we do the conditional probabilities, first step, we need to order all the observations. Then each conditional probability will conditional on previous observations. So vector approximation in spatial settings simply means when we condition on past observations, instead of all the past observations, we only condition on nearest neighbors. So in this way, the covariance matrix become much smaller because only depends on the number of locations we condition on. So intuitively, this is also related to Gaussian Markov random field. By conditioning only a subset of the neighbors, we introduce zeros in the precision matrix. So vector approximation actually induces a sparse precision matrix, which is a covariance matrix inverse. So the vector log likelihood, instead of a full complete conditioning set, we only select a subvector. So by doing this, the computation is substantially reduced. So in this, in the following project, I will use M to denote the size of the conditioning sets, which is the size of neighbors. Here is a simple illustration of vector approximation algorithm. So suppose we observe 8 observations. So first we order them from 1 to 8. Now suppose I want to find the conditional probability of location 6 given all the past locations. Since if the full likelihood requires the Y6 conditional Y1 all the way to Y5. Now, if I only keep 2 nearest neighbors, so instead of 1 to 5, I only keep the location 2 and the location 5, these 2 observations as the 2 nearest neighbors of 6. Then in terms of computation, this covariance matrix inverse, the covariance matrix instead of dimension 5 is reduced to dimension 2. So as you can see, the different ordering algorithm also play a role in providing candidates for the conditioning sets. So for example, here, if I use Morton ordering, the 2 nearest neighbors of location 6 are 2 and 5. if I use the random ordering, when we construct a conditional probability, the two nearest neighbors selected are 3 and 4. So when the data set is large, the different ordering may lead to different nearest neighbor, also may affect the approximation quality. If we consider vector approximation in terms of memory, instead of n square memory requirement, we only need a n m square. M is the size of the neighbors. Then computation also can be reduced from n cube to n m cube. So this m typically is very small. Is from the graph you can also see the computational time and memory is actually close to linear. Okay, so for vacuum log likelihood, we realize that it involves many independent computational tasks. There are small tasks, but there are a lot of log conditional probabilities here. So this, we have a lot of computation tasks, but they are lightweight. So that inspires us to use the batched operation to parallel this lightweight task on GPUs. So basically that's the main contribution of the development for parallel vector. We introduce back operations to parallel these log conditional probabilities on GPUs. So here we start with one GPU. Then the K plus routine and CUDA are used for the batched kernel computations. So for this software, a batched implementation of vector algorithm on GPUs is available on GitHub. And we show that the speed up of the proposed framework achieves 800x to more than 1000x compared to the exact solution. And we can consider pretty large problem sets, up to 1 million geospatial locations on a single GPU while maintaining the accuracy. So the first paper, the contribution is mainly about implementation on using HPC. Then the second paper is more statistical contributions. We investigate the approximation quality. Later I will give the reference list. So then we move a step further. In the first vector approximation I introduced, I will call it a classic vector, CV. And so for example, when I construct a conditional probability of Y6 given the 3 nearest neighbors, and the conditional probability of Y9 here given the 3 nearest neighbors, we realize that if these 6 and 9, they are close enough, they may share some common neighbors. So if we calculate this conditional probability separately, it causes the redundancy in the classic decomposition. So in the second project, we propose to do grouping, to do clustering first, to define blocks first, then to find the nearest neighbors for the whole block. So this is why we call it a block vector approximation. So BV refers to block vector, means I first group these two observations together. Then when I construct the conditional probabilities, I will find the nearest neighbors for this group. And CV refers to classical vector. Then I will do some comparisons a little bit later. This block vector approximation, as you can imagine, this conditional probability in terms of approximation is not as accurate as classical vector. But because we use block, the number of conditional probability is smaller, so the computation is faster. So the block vector approximation is more computationally efficient than the classical vector. And the software, we call it a parallel block vector GP, which is available on GitHub as well. Using block structure, we are able to consider larger conditioning size and the block count. If we consider larger block counts, means the block size is a little bit small, then the approximation accuracy is a little bit better because it's closer to the classical vector. The block vector method demonstrates an approximately 80x speed up and 40x larger problem size compared to the classical vector algorithm. So when we consider much larger problems, block vacua definitely has a computational advantage. So then the next contribution is we consider more than one GPU, multiple GPUs. So the motivation from Gaussian process is from computer experiment. As we know, in computer experiments, Gaussian process emulators are widely used. So typically, the Gaussian process emulators is computer experiment. The observations live in a higher dimensional space. The classical data sets can be billion level and high dimensional problems. So for such setting, there are two challenges, and we gave two solutions. So the first challenge is for computer experiment, typically we have a high dimensional input space. So when the dimension is high, it's very difficult to define distance. So because vacuum approximation in spatial setting highly depends on how to select neighbors. So the nearest neighbors turn to give a better approximation accuracy. But in high dimensional setting, how to define the distance or how to find the neighbors to construct this vacuum likelihood is a problem. So this one, we need to modify the covariance functions. So the modified covariance function I will introduce later. We need to introduce additional parameters actually to scale each dimension. Another problem is when the problem size is larger, we need to make use of multiple GPUs. And how to do the parallel computing, how to distribute the block vector algorithm on multiple GPUs efficiently. That's a major contribution to HPC. So here is the scaled covariance function I mentioned before. This is modified version of it. So here, f is a covariance function, and here this beta is something new here. We call it a scale parameter for each dimension, because before we have only one beta, one scale or one range parameter. So when the dimension is high, become d. For each dimension, we need such a parameter. So 1 over bi, this quantity is defined as the relevance of the ith dimension. In computer experiment, this quantity in practice is important, because once we feed a high dimensional Gaussian process to the data from computer experiment, this relevance can tell us which dimension is more relevant to the output. So here is a just illustration of different step, each step of this distributed scaled block vector. So as I mentioned, the scaled refers to the covariance function, and the block vector is the block vector I introduced before. The major challenge and the problem we solved is actually how to divide the data to different workers, and how to define the nearest neighbors with minimum communication among those workers. So for example, when we choose the nearest neighbors, we could have a threshold. We only search the distance within this threshold to reduce the computations. Just to illustrate this scaled block vector for applications, I will talk about one simulator. We built a Gaussian process emulator using the data simulated from a Meta RVM. So Meta RVM is a simulator that models the spread of respiratory viruses with input variables summarized in this table. So simulator, typically the modeling is forward. So in the computer experiment, you have all these input space, all these input parameters. In application, we know those parameters should be important, but this not necessarily very always important related to the output. So when we fit a Gaussian process emulators, the relevance I mentioned before, if we have the estimate, we can understand which input dimension is more more important to the output. So here, the data simulated from the simulator, we have 50 million sets of random generated input values. Then the output is the accumulated number of hospitalization over 100 days. So each location in this setting is live in a 10-dimensional space. Okay. So this is the estimation results from this application. As you can see here, I listed, I plotted the relevance, which is 1 over beta, using different conditioning sets. So when m equal to 100 means I only consider 100 nearest neighbors, and 400 means I consider 400 nearest neighbors. So it's interesting that here, the DH/DR, these two dimensions, the relevance of DH and DR are close to 0. If we come back to the table to see the DH and the DR are the mean durations in the hospitalized state. So because our output is about the numbers of hospitalizations, so we didn't really consider how long the patient stay in the hospital. So that's why these two dimensions actually are estimated as not relevant. The second plot here shows the prediction errors. So as we can see, if we consider using larger conditioning sets, then the estimation and the prediction approximation accuracy is better. So the spatial, the prediction errors is smaller. So when we increase the conditioning size, the prediction error is reduced. Okay, so the last analysis we did is about power consumption by running the vector approximation on GPUs. So the first plot is about 2 million, 2 million points, and the second plot here is 5 million points. The first row is when we use the nearest neighbor 100, and the last one is 400. As you can see, when we increase the conditioning sets, we need more energy to complete the computations. So for 2 million points, when m equal to 200, the energy cost is 41.5. Just as a reference, full charge of iPhone 16 is about 64 kg. So that's relatively the energy cost if we use 200 nearest neighbors for 2 million points when we fit a Gaussian process. So as you can see, this skewed block vacuum assumes around 0.5% of the energy compared to the exact GP, and while handling much larger problems. So the software is also available on GitHub. We call it a parallel skewed block vacuum. So the skewed version, because we consider higher dimensional GP, and the main contribution is about multiple GPU computations. Okay, so for the rest of time, I will briefly mention some of the efforts we made using deep neural network for spatial prediction problems. As we know, in geostatistics, kriging is commonly used for spatial prediction. The features of kriging prediction include it provides a best linear unbiased predictor, but it involves modeling the mean and covariance function of spatial process. So the drawback is the same. It typically computationally expensive, and also we know if we have a Gaussian process, kriging is the best predictor. But if we don't have a Gaussian process, it's still a best linear predictor, but may not be optimal for non-Gaussian data. On the other hand, deep learning provides a computational scalable methodology for a variety of data types and a non-linear prediction. So that's why we were thinking, can we actually borrow deep neural networks to have a non-linear spatial predictor? During this research, the first question we asked ourselves is why classical deep learning method cannot be directly used for spatial prediction. Because we realize in real applications, observations are often spatially sparse with inadequate spatial coverage, and typically in spatial setting, we don't have many replicated spatial data. Only a few covariates, this is so-called features in machine learning language, are observed at the location to be predicted. And also the spatial the processes typically exhibit spatial dependence. So our first research goal is to develop a deep learning-based methodology suitable for spatial prediction. Once we have a space-time, a major goal is to provide a forecast. So in statistics, since we are interested in the distribution and uncertainties, so the probabilistic forecasting, this is something we want to solve using deep neural network. Probabilistic forecasting is beyond a single value or point forecast. It's about distributional forecast because it involves extrapolation, so it requires some special treatment. So for the second project along this line, we developed a deep learning-based methodology suitable for probabilistic forecasting. I will just spend a little bit of time to talk about the settings. The rest will come naturally. In spatial setting, if we consider n observations, S1 to Sn, and the predictor of a deep neural network at a new location S0 can be written as this is unknown function, which is learned through the training. And this little x are the covariates observed at different locations. And the theta here are the parameter from a deep neural network, those weights and the biases. And the theta hat is estimated or trained through the model training. So here L is a loss function, and the X here are the data. So we find which set of parameters can minimize this function value and the observations. So this is a trained deep neural network. After the deep neural network is trained, we plug in the new location with covariates, we get the prediction. So this is my notation. I call it a predictor of a deep neural network. So how to account for the spatial information in these features? A natural way is to just add the coordinates like longitude and latitude to the features. But the problem is the final predictor can be a very complex functions over the longitude and latitude. It may not be easy to converge. So inspired by the spatial random field representation, we borrow the idea of spatial basis functions. So the idea of deep kriging actually is simple. Rather than only including the spatial coordinates in the features, we first construct spatial basis functions. Then the spatial basis functions can serve as a we call it an embedding layer in the network before we pass the data to the hidden layer. So here's the visualization of deep learning structures in 2D spatial case. So here are the coordinates. Then we first construct an embedding layer, which are the spatial basis functions, together with all the other covariates we observed, we pass through the deep neural network. So as you can see, the main idea of deep kriging is to transform spatial prediction problem to regression problem by introducing the spatial basis functions. For space-time, the network we used for forecast is LSTM, long short-term memory network. Since LSTM is designed for time series, we also propose a convolutional LSTM to be able to use the neighboring locations when we do the temporal forecast. Okay, so for probabilistic forecasting, the thing we changed in the LSTM is a loss function. So instead of L2 loss, we introduced the quantile-based loss. So this is a check function commonly used in quantile regression. So when tau is equal to 0.5, we have the median. When tau has taken other values, we get a quantile estimation. So we also need to modify the activation function to avoid the quantile crossing. Okay, so this method proposed for spatial-temporal data set won one of the computation we organized in KAUST in 2022. There are like 20 research teams worldwide registered for this competition, and this spatial-temporal deep kriging won the space-time setting. So there are 22% and 9% improvement over the second best. All the competitors include vector approximation, GPGP package, which use vector approximation and the block composite likelihood. Because the dataset itself actually generated from a Gaussian process. I think because the dataset is large, the approximation may make those methods maybe not perfect because of the approximation. But deep kriging is basically non-parametric based on deep neural network. The performance is better in that setting. Okay, so the last few minutes, I will just show one data example. So here, space-time data I considered is PM 2.5 in the US during one period, is monthly data. And here is the plot. So for example, December 2021, those are the observations from the US, and the second one is June and December. So the second row are the spatially interpolated PM 2.5 map. And the last row provides the 90% prediction interval from LSTM with quantile loss. So I can predict the quantiles, then I look at the coverage with 90%. So this is the length of the 90% prediction intervals. For forecasting, we forecast for the first 3 months of 2023, and this is the forecasted value, and the second row gives the forecast interval. So just to have a better visualization, I just pick one location from the PM 2.5 dataset. So this one is San Francisco. I use the Q quantile LSTM, means a quantile convolutional LSTM. Quantile loss and convolution means I use neighbor observations to help me do the temporal forecast. So the dark blue line is interpolated value using spatial-temporal deep kriging, and the light blue line is the quantile estimate when tau equal to 0.5 is a median. And this red line here are the forecasted value, and the black dots are the left out observations. So as you can see, the prediction is pretty accurate, and the gray area provides the prediction interval. Okay, so with this, I will stop. So I listed a few references I presented into this talk. So the first one with my former students, Qilong Pan and research scientist Samei, and also colleagues from KAUST. That's the first project we developed using GPU for vector approximation of Gaussian process for univariate geospatial data. And the second one is the actual geostat I mentioned before for exact computation. The third project is more statistically oriented. We proposed the block vacuum for Gaussian process approximation. Then we mainly studied the statistical efficiency in such approximation. Then the next one is the skewed block vector approximation using multiple GPUs. The last two papers are related to deep kriging. The first one is univariate spatial data, spatial only. The second one is spatial-temporal with two-step procedures. So first, the spatial interpolation, then temporal using LSTM or convolutional LSTM for temporal forecasting with quantile loss to provide a predictive distribution. So with this, I will stop. I give my outline here. If any questions, please feel free to ask. Thank you very much.
So thank you so much, Ying, for a very wonderful presentation. You did a lot for HPSC. Uh,
Thank you.
so we have 10 minutes for Q&A. If you have any questions, feel free to unmute yourself or you can put it in the chat. Are there any questions from the audience? While you're thinking about your question, I have a question. So for all the packages that you have on GitHub, do you have some tutorials how to get started with them? And do they also come with those large data sets so that we can try?
Those software come with the publications. I think Sami and Qilong, they are doing some software engineering part to make it more practically useful. Yeah.
Okay, so there is a question. Will we get the recording or the PowerPoint slides? Yes, we will post it on our website, and the recording is also going to be on YouTube. Are there any other questions?
Hi, can I ask a question?
Sure.
Sure. Hi.
Sorry, I was trying to see if my video start. Yes. Okay,
Yeah,
perfect.
I just saw you earlier today.
Yes, thanks for the talk. I was wondering because you were kind of saying, I mean, all of the first part as well as the second part was, talking a lot about computational complexity. And I was just wondering, you didn't really say very much about the costs of sort of training, like the LSTM or the other sort of deep learning approaches. Can you maybe compare a bit how they, just how they compare a little bit in terms
Yeah,
of cost?
in the paper there is some extra time we actually provide actually for the problem we have considered. But yes, I think for training it's very hard to quantify the computational cost. So for example, when we won this competition, that because it's competition, so my students spend more time in tuning, like about 8 or 9 hours just for tuning, because he said that's one time competition, he need more tuning. Yeah, but I think in theory it's very hard to quantify. Just for the problem we considered, for this problem, the training, how much time it costs, that we reported in the paper. Yeah, but once the training actually takes the most of the time using deep neural network. So once it's trained, the prediction is very fast.
Okay. Yes, thanks. But
yeah,
so sort of the training like is sort of significantly more expensive than the sort of direct approaches that you were talking about in the beginning.
for fitting a Gaussian process is still much more much slower. I think I was talking about even the training prediction for millions of data, just the training I think for 1 million is like 8 hours, something like that.
Okay.
Yeah, but for smaller problem is much faster.
Okay, thanks.
My experience is actually for real application, we tend to find deep clicking perform better. I think one reason is for real problem, we don't have this true Gaussian process there. And for large problem, it tends to work better because deep learning is in general, we have more data. The training, you will basically learn more information from the data.
Okay, thanks.
Yeah.
Are there any other questions? So if there are no questions, then let's thank again Ying-sun for today. We will send out announcements for our next presentation. It's going to be Lisa. I think we have her on February 19. So yeah, just watch out for those announcements.
Yeah, Mary, just I saw one question. If
Oh, there's one question. Okay.
quickly answer this.
Okay,
probably.
Cosmo. Let me read Cosmo's question. Do these methods give objective uncertainty quantification in terms of coverage?
So I mentioned for the spatial spatio-temporal deep kriging, we use probability forecasting. So basically what we are doing is to provide predictive distribution. So because if we know the quantiles, we know the distribution already, then this interval is provided by the coverage. So if I consider 90% prediction interval, I will give the, if it's symmetric, I will give the upper quantile and the lower quantile. That's the lower bound and upper bound of the prediction interval. So it's not a real uncertainties because spatial-temporal deep kriging has two steps. So the first step is spatial interpolation because the LSTM, when we do this convolutional LSTM, has to be on the grid. So the uncertainty, the final prediction interval does not consider the first step uncertainty. It's not a real full uncertainty quantification, but we can provide prediction intervals, not only a point prediction. Thank you.
So no more questions, or is there more? Software is available. Yes, it's on GitHub, and you can see the links to those
Yeah,
software.
and also some posted in the chat all the links again. Right.
Okay, we have 3 minutes more, so let's just wait for some other questions. There's another one from Hadika Tahir. In applied environmental health studies, where spatial models are often used to generate individual level exposure estimates that are then fed into health outcome models, how do you see tools like Vecchia GP or Exageostat fitting into that pipeline?
Spatial model used to generate individual level exposure estimates. I see. Yeah, I think I know for some health studies. So, for example, some health models need input from I don't know what kind of individual level exposure. I think those things, if this spatial individual level exposure estimate involves Gaussian process models, then the Vecchia can be used as approximation to speed up this process. If that's I think this Vecchia approximation is a very general idea as approximation of a Gaussian process. Whenever your model has a Gaussian process computation, which you cannot handle, you want to have a approximation method for fast computation. This Vecchia GP can be used there. And I just want to emphasize this Vecchia GP itself is not new. The new thing we contribute is a GPU implementation. So basically, we have a GPU version of Vecchia GP. So Vecchia is a very old topic, idea, but very useful in terms of Gaussian process approximation.
Any more last minute questions before Ying leaves? If you have other questions to her, you can just email her. Okay, it's 9 o'clock on the dot. So thank you so much, everyone, for joining us. See you again next month. Bye-bye.
Thank you for joining me. Bye-bye.